Yeah, so good evening. So today I'm Calvin Joseph and I'll be conducting the summary session for this digital control and switch mode power converters and FPGA based prototyping, which is taught by Dr. Santanu Kapoor of IIT Kharagpur. So today we will be just having a recap and I'll be discussing about digital voltage mode control, like the basic control strategy which is used and on which you can build your understanding. Then I'll be also touching a little bit on counter-based DPWM and then I'll also talk a bit about mixed signal current mode control and for about the current sensing which is required for it, bidirectional current sensing. One setup I'll show. Then we will be going for the questions. So this is digital voltage mode control, and this is a buck converter. This is my buck converter stage. This entire thing is the buck converter. That is the hardware thing. So, and the output voltage of it is sampled by an ADC, analog to digital converter. And that has a delay. There's a delay in the ADC, and that is compared with my reference, which generates my error, which passes through my controller and generates my control signal. So that control signal is compared with my ramp, okay, with my counter ramp. And that will generate the instant when I must trigger the reset. And the set pulse comes periodically, and that generates my gate signal Q. So this is a very basic overview structure of DPWM voltage control. So we will consider now the main issue here is when should we take the sample of the output voltage. When we take the sample, that depends. So we will consider the case where there's uniform sampling. So this is a case of fixed frequency. Okay, this is fixed frequency control because it is being turned on and off, turned on at a fixed rate, So it is fixed frequency control. All right. And let us consider, so this is my switching clock, this is my sampling clock. And this is my output voltage graph, and this is my inductor current trace. And this is the ramp, the counter ramp signal over here. This is my ramp signal over here, and this is my output Q. Okay. So this is my output voltage is in analog domain, as in the actual setup it will be. But I am taking the sample over here. So I take the sample of it over here. When I take that sample, I will update my controller. Output gets updated. And with the updated control value, my on time is generated. So effectively, I'm controlling my duty ratio. Effectively, I am controlling the duty ratio. So in this case, what happens at the switching clock? When the switching clock comes, this clock comes, my sampling clock also comes, and the sample of the output voltage is taken, and that updates my controller output, and that generates my new duty ratio T on 1. Okay, it generates a new duty ratio. Similarly happens in the next cycle. Now let us consider a case when there's some delay. So what we do is, this is my switching clock, which is coming at its repeated duration. But now we have a sampling clock, which is like what you say, it is advanced. It is earlier. The sampling clock comes earlier than the switching clock. So effectively, the sample of the output voltage is taken when the inductor current is falling. That means when there is a falling, when the inductor current is falling, that is the main switch is off. And it is like either freewheeling through the diode or freewheeling through the synchronous MOSFET. That time I am taking the sample of the output voltage. So that is known as interval 2 sampling. Interval 2 sampling is when we are sampling when the main switch is off, and interval 1 sampling is when we are sampling when the main switch is on. So in this case, we have to do interval 2 sampling. So I am taking the sample of my output voltage, and that generates my, and I have taken the sample over here. But my update of my controller signal is happening after this TS time. So that is why there's a delay. Okay, and this we consider because there's a ADC conversion time, etc. To model that, we do this. Okay, and when after it gets updated, then it will generate my new duty ratio. Similarly, that happens in the next cycle as well. So we are here doing interval 2 sampling. That TS time delay. Then there could also be a case that we are taking one complete cycle delay. That is, I'm taking the sample output sample voltage over here. I'm waiting for this long duration, and after that long duration is over, I am updating my controller signal over here. So there is an effective delay of time t for updating my controller, updating the control output of the controller, although the sample was taken one cycle prior. So because of this delay, result in one cycle, it is known as one cycle delay, and that will reduce the stability of your control. So the more and more you delay to do things, more and more difficult it becomes, right? In life also, if there's a task be delayed to do it, it becomes more hard and difficult to do. Similarly, in this control system, as you increase the delay, it will reduce the effective phase margin which is possible. And so when the phase margin is reduced, your stability becomes poor. So, but there is a delay. In certain cases, we need to have this one cycle delay. An example is fully digital current mode control, where this delay is has to be there. Okay, so we are not looking into that, but I'm just telling that it is required in some cases. Now I will be. So, is there any doubts still here? Everyone is following? Okay. So, I'll proceed with counter-based DPWM. So, to implement that this SR logic, this logic of this, okay, to implement this logic along with this, okay, along with this, we use a counter-based DPWM. So, what is my counter? That the ramp, the ramp is implemented using this. Okay, so this is my ramp which is happening, and to increment, that increment happens periodically at a time period of t clock. So there is a f clock signal over here, and it comes periodically after a time period of t clock. Okay, so this is this f clock which is there. So this f clock needs to be a very high frequency so that it can increment it. All right, and when there's a certain maximum value. Okay, so this is for when the greater than or equal to comparison, etc. All these things are there. So this will generate my effective gate signal. So this is my control signal VH of n, which comes via the controller. Okay, so when my this counter signal goes above that, okay, that time my switch turns off, my Q turns off. Okay, so this is how you are implementing from a counter, implementing the digital pulse with modulation. Right? Now, if we have an n bit counter, now we have a counter of n bits, then my clock signal should be of this frequency, okay? This frequency. F clock should be equal to 2 raised to n into FSW. Now, what is the resolution? Okay, so this will has certain resolution with the whatever possible duty cycle it can generate. Okay, see, in this case, it can either generate duty ratio up to this, or it could add this much of extra duty ratio, or this much of duty ratio. So there is a certain unit level of duty ratio that can be generated from this counter-based DPWM approach, and that is known as your duty cycle resolution. So this duty cycle resolution is dependent upon your delta T DPWM upon TS. Okay. Now, in case of counter-based DPWM, this delta T DPWM is just equal to your T clock. Okay, this is your T clock. This is your actually delta T DPWM. Okay, that is actually your T clock. So that is why your QD is actually just your T clock upon TS. Okay, so that is your resolution. The resolution which you can obtain using that n bit counter based approach. Okay. And I'd like to point out one more thing is this NR can be a value, okay, but the NR should be less than 2 raised to n. Okay, NR should be less than 2 raised to n. Then only it can be the n-bit counter can implement it. So suppose it is 9-bit 9-bit counter. So if it's a 9-bit counter, then 2 raised to n will correspond to 512. So NR should be less than 512. Okay, NR can be less than 512. So my NR can be like say 300. Okay, it can be 300. But still, this duty cycle resolution capability is independent of the value of NR. Okay, it is independent of the value of NR. It is not that if my NR is smaller, it will be able to give more resolution. If my NR is larger, it would be able to give more resolution. For a particular n-bit counter, this is the resolution which is possible for you. Okay, so this is the thing for counter-based DPWM. Now, I'll be just talking about mixed signal peak current mode control. So, in mixed signal peak current mode control, your current loop is in analog domain. Current is in analog domain, and your voltage is in digital domain. So, the same procedure output is sampled compared with VREF. The error comes, it passes to your controller that generates your IREF. That is passed to a DAC to generate a corresponding reference current signal. That reference current signal is compared with your actual inductor current signal, and that results in when, at what extent your reset signal comes in terms of your Q. Okay, so and this Q comes periodically at a rate of FSW. So this again is a concept of fixed frequency. This again is fixed frequency, and this is for peak current mode control. I effectively, so this is my reference, I reference, and this is my IL. Okay, so effectively I'm controlling the peak of my inductor current. Effectively I'm controlling the peak of my inductor current. Okay, so this is one cyclic diagram. So this is my inductor current, this is my output voltage. So I take the sample of the output voltage prior. So this is my switching frequency clock to turn on my gate signal. Okay, so this comes over here. Before that happens, TS time prior to that, I will take the sample of my output voltage. I take the sample of the output voltage over here, and I give TS time delay. This TS is the time I have provided for my controller to process that sample and generate the ADC to process that sample and generate a digital value corresponding to the sample, and then that will pass through my controller, which has its own number of computation cycles, etc., to generate my reference value, and my reference value gets updated over here. So this much is my delay. Okay, so my reference value gets updated over here, and that reference value is used in this cycle to determine the duty ratio. That reference cycle is used in this cycle to determine the duty ratio. So similarly, for the next cycle, I will take the sample again TS time prior. I'll take the sample of the output voltage here, and I will give this time TS for both my ADC conversion time as well as for my controller computation time to generate an updated reference value at this instant. Okay, and that will be used in the next cycle for generating the next duty ratio. Okay, so this is how mixed signal peak current mode control is implemented. So it is again trailing edge modulation, and here again it is interval 2 sampling, because I'm taking the sample over here when the switch is off. Okay, when the main when this switch is off, that time I am taking the sample, and so it is a case of interval 2 sampling. So one good way to remember is for peak current mode control, it will be trailing edge modulation and interval 2 sampling. For valley current mode control, it will be leading edge modulation, and it will be interval 1 sampling. Okay, so this is something you must know. Okay, you must keep it in your mind so that you will be able to understand and remember it.
Sir, here to
Yes.
Sir, here to this V0N sample which you are taking,
Mm-hmm.
yeah, there.
Mm-hmm.
The corresponding gate pulse is generated only here, in this location, right, sir, after TS.
No, not the corresponding gate pulse, the corresponding reference to generate the gate pulse. Okay. V output is sampled over here, and then the reference is updated over here, okay, at this instant. And once the reference is updated, then that reference is used in that cycle to generate your duty ratio.
So here we are not taking before TS period to generate the duty cycle.
See,
Actually,
what,
sir,
that
actually, what I'm saying is the sample which you are taking here
yes,
is actually the gate pulse because of this. Okay. Now the gate pulse because of this is this one only, right, sir?
yes, is correct. Yeah. Okay, so we are just aware. Because it is a causal system. It's not like you know already what should happen and you do. This you take a sample and then you from that sample you realize what you have to do next or what change you have to make. Okay, so I'm taking the sample here, waiting, giving some time TS time delay, which is required. Okay, and it's not that instantaneously everything can happen. There is a delay. The delay might be small, but the delay is there, and for safety and for your own you must have that guarantee that I have taken the sample at this time, and it is guaranteed, even in worst case condition also, that it will be able to generate a reference by this time before the switching frequency clock comes. Okay, so by that way you determine how much delay is required. Okay, and then you use that computation of that to generate your new duty ratio.
So I confused between the small TS and the capital Ts. Okay.
So capital TS is your time period. Okay, so proceed. So now I'll consider mixed signal constant off time. So again, this is constant off time. It is peak current control. The only so till here, from here till this part, all are same. Okay, all are same. So it is, remember, this is peak current mode control, which was same as the prior one. The only difference is this is constant off time. Okay, constant off time. So my off time is fixed. My on time is varied. My on time comes is generated from my controller. Okay, and that's why, because the on time varies, it is a case of variable frequency. Okay, it is a case of variable frequency control, right? So when the edge comes that my inductor current has exceeded my reference current, then that positive edge comes, that is detected. Then the minimum on time is there. After minimum on time is over, there's a monoshot timer. No, this logic is a bit wrong. There's a monoshot timer which will be off for that required off time. As well as we must also make sure that a minimum on time logic is present, so that even though the positive edge comes, it will not, just turn it off, etc. So that logic is present, and that will with that required dead time, it will generate your high side signal and low side signal. Okay, so this is how constant off time peak current mode control is done. And it is, and in this is again peak current mode control. So it is we will have to do interval 2 sampling. That is when the inductor current is falling or when the main switch is off. That time we are taking the sample of the output voltage. Okay, yeah. So this is the case that over here the output voltage sample is taken over here, and the reference is updated over here. Okay. So again, there's an interval 2 sampling with TS time delay. It's like when the inductor current is switching off. Okay, the inductor current is like still falling. That time you're taking the sample, and then you're turning on the say you're turning on the switch, and it remains on until it reaches the reference value. That is the way. And you're taking the sample over here, but you're updating the reference over here. So that's why there's a TS time delay. So now we have talked about current control. Now we will talk about current sensing. How do we sense the current? Because only when we have the sense, we just directly will not be able to get the current information. We need to have a sensing technique to sense the current. So for that, a very popular approach is your resistive current sensing. So this actually is the circuit of a buck converter. If you see, this is my input voltage, this is my input capacitor, this is my high side switch, and this is my low side switch. After that, there's my inductor, and there's my capacitor, and there's my load resistance. So this is a buck converter. But in the series path of the inductor, I place a small value shunt resistance, okay, shunt resistance. And across this shunt resistance, I will connect a differential amplifier, okay, a differential amplifier. So if you know, so the voltage over here is Vx minus Vy. So Vxy, which is equal to Vx minus Vy, is equal to the inductor current into R shunt. Okay. Now my sensed out, this IL sense signal is equal to the gain of my differential amplifier into this Vxy. So what is the gain for differential amplifier? It is actually equal to Rf upon Ri into Vxy. This is the resistance Rf, this is the resistance Rf, and this is Ri. So it is equal to Rf upon Ri into Vxy. Okay. So that is equal to Rf upon Ri into R shunt into IL. Okay, so this is effectively my current sensing gain. Okay, so this is my current sensing gain. Now you may like this is the case, okay, and VCC will be like say around 5 or some value. This will be some minus 5 volts something. So my inductor current can swing between 5 volt and minus 5 volt. The sense inductor current can swing. But in case what was happening is you just want that current, you just know that current is only flowing in this direction. It will not flow in the opposite direction. Then your VEE, you can set it to be 0 volt. Okay. And if it is 0 volt, then it will only give output between 0 to 5 volt. And in case your inductor current goes in the opposite direction, it will not, your sensed signal will not be able to detect them. Okay, so that is the case. So if you want to have a bipolar output from an op-amp, you need to give it a bipolar supply rail. Okay, that is, it should have a positive supply and a negative supply as well. Okay. The another important consideration is when you're doing this sort of current sensing, you must see this is my current signal. Okay, this is my inductor current signal. Okay, and this is my time period, and which has a corresponding switching frequency. Now, this current signal is a periodic signal, right? So if you do Fourier series, this current signal is made up of a DC term. Okay, the first harmonic that of switching frequency, then it has the third harmonic, fifth harmonic, etc. All these harmonics are there. So if I want this signal over here, I need to have the DC first, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, all these harmonics information I must have so that I can reconstruct this signal, okay, the original signal. But okay, so that is a requirement. Now, to reconstruct to a fairly accurate degree, it is sufficient to have the information till the ninth harmonic. It is sufficient to have the information up till the ninth harmonic. So of course, because you would know that as the harmonics increase, the magnitude of the harmonic reduces, and its effective contribution to the signal is negligible, can be neglected. Okay, and you must take care that its effective contribution can be neglected. Okay, so for this to happen, you must make sure that the bandwidth, okay, the bandwidth of your op-amp should be greater than 10 times your switching frequency. The bandwidth of your op-amp should be 10 times greater than your switching frequency. Another important thing of your op-amp is there's a unity gain bandwidth or gain bandwidth product. Okay, so that suppose is 2 megahertz. Okay, your gain bandwidth product. So if now your gain is made, this is for unity gain, but now suppose your gain is what determined by RF upon RL. So suppose I make my gain to be 2, then my new bandwidth of my op-amp will only be 1 megahertz. because my gain bandwidth product 2 into 1 megahertz, that is fixed. Okay, that is fixed by the design by the op-amp. Right. So now if I increase the gain, I make the gain 2, the bandwidth of the op-amp can reach maximum up to 1 megahertz. Okay, so that is another important consideration you must take into account. And when you use these sort of, these resistors, it is advised to use those resistors with a very low tolerance, okay, low tolerance, so that they are quite accurate. Because if there are any inaccuracies in it, it would, your sensing gain will change. You do not know the exact value of sensing gain. So it is best to use good quality sensing resistors. And you'll have to generate these supplies, this VCC, VEE, you'll have to generate. So these are known as auxiliary supplies. So although your buck converter or boost converter is actually a power supply unit, okay, they are like regulated power supplies for its own, for its running and operation and sensing everything, you need to also provide it some small auxiliary supplies. So all these other auxiliary supplies are required for all these things. For this, then for your your FPGA also requires a supply. So this is for your op-amp for current sensing. Then your gate driver also will require a supply. So when you are actually making a board, you have to consider all these things. So like you must consider that you're generating a 5-volt supply. So that 5-volt supply can be used for your gate driver. Right? If your gate driver requires another voltage, then what you have to use a resistive divider to step down the voltage or etc. Also another concept of isolation also you'll have to consider if you're using an isolated converter or if you are using isolated sensing. So these aspects will come in the hardware aspects, which when I hope you will consider when you're making a PCB or a hardware prototype board. So now we are actually doing digital control. So
Sir?
this code, yeah, yes.
Sir, here we have to the bandwidth of op-amp. We have to ensure it is greater than 10 times FSP.
Yes. If not, your
Sir, this
yes, tell.
okay. If it, then only I will get the current IL sense closely equal to IL, right?
Yes, yeah. So this suppose this your active current signal, and this your your sense signal will be something around like something like this, something like something will be something like this and something like this, something like this and something. It will what I mean to say is it will not exactly match. Okay, it will not exactly match because the high frequency components are for these things like the high frequency components are for the sharp transitions, etc. Something like that. Okay, so it will not have that exact way. So, and it is also not very much required. You just need to have a signal which has a shape close to the original input signal. Okay, the sense signal must have the shape close to your close to its input signal, close to the signal which it is sensing. Okay, and for that, the standard thumb rule is the bandwidth of your sensing should at least be 10 times your switching frequency.
Sir, this unity gain, this gain bandwidth ratio we are taking.
Unity gain bandwidth product, yes.
Sir, what is the significance of gain bandwidth product? Sir, what is the significance of this one?
Significance like that I haven't thought about, but that is there. Like that is one of the main things in the data sheet of the OpenAI you have to consider while selecting an op-amp. Okay. So that.
No, sir. In our circuit, at least.
Yes, in your circuit.
For our IL, for our sensing the inductor current, how this gain bandwidth ratio is useful, sir?
No, like suppose your switching frequency was say around 500 kilohertz. Okay.
Okay.
So your and the gain, your gain, suppose your gain, I'm just saying was 4. Okay, your gain was 4. So, and you have unity gain bandwidth of 2 megahertz. Okay, So the bandwidth of your sensing will be 2 megahertz by 4. That will be equal to 500 kilohertz. 500 kilohertz. So in this case,
Okay.
your sent signal will not be of the shape of your inductor current. It will have certain other shape. Okay, so that would not be very what I mean to say. It won't be exactly reflect your inductor current. It won't reflect to a good degree your inductor current, and it will not be sufficient. Like another thing is there's noise. Okay, there's noise will be there, and other things will be there. So it would not be sufficient for you to control. There will be issues in controlling it. And another thing is like sensing is a very difficult thing to debug. Like your control is useless if your sensing is bad. Okay, you might have very good controller, you may do all the sophisticated controlling things, algorithm you can make. But if your sensing signal is poor, that is your input signal to your controller is poor, then it will generate performance will obviously be poor. Okay, because if you want your send signal to say to be like it was coming around should come corresponding to 2 volt, but it came out to be 1.9 volt. So your controller will consider that it is 1.9 volt, and it will do its computation based on that sense value 1.9 volt, which is actually erroneous. So then the output of your controller also will be erroneous. Okay, so that is why sensing is like it is quite an important thing. You must spend sufficient time to get it right.
Gain bandwidth, this gain is equal to this RF by RSH, RA into RSH. Is it, sir?
The gain of your op-amp. Okay, the gain of your op-amp is RF upon RI. This is your gain. This is your gain of your op-amp. Okay, this is the gain of
the
your
gain bandwidth product. Okay.
So the gain bandwidth product.
The gain bandwidth product. Is this the same gain coming here also, sir?
No. Like
RF by RA is the gain.
No, your gain bandwidth product. So let me write it. Your gain bandwidth product is a property of your op-amp. Okay, this is a property of your op-amp. It is given in the datasheet. I have been given in the datasheet that the gain bandwidth product of this op-amp is 2 megahertz. Okay. Now, based on the external circuitry, I am setting the gain of my op-amp to be RF upon RI. Okay, I'm setting the gain of the op-amp to be RF upon RI. If I've set this gain, then the bandwidth of my op-amp will then be the unity gain bandwidth product divided by RF upon RI. So the bandwidth of my op-amp in this case would be unity gain bandwidth product divided by RF upon RI.
So this is the okay. Now we can now this is the bandwidth of op-amp because of this gain. The bandwidth of op-amp has reduced.
Yes, exactly.
So this is unity gain means when the gain is 1, this is the bandwidth.
Yeah.
Okay. Okay.
Yes. Now we are going for digital control. So digital control, so we have to represent our analog numbers, our digital or our integers have to be represented, right? So suppose you have this value 0, so that is represented in straight binary using these set of bits. Suppose you're considering 3 bits, okay, 3-bit representation. So this is the simple representation of digital numbers which we all know. Okay, if you want to convert it into 2s complement, then for positive values it remains the same. For the negative value, you have to just invert it. So suppose 2011 is for 3, for minus 3 it will be 100. Okay, minus 3 will be 100. That is 1s complement plus we have to add 1, so it becomes 101. Okay, so that's how we get minus 3. Now, if you want to convert to offset binary, then what do we have to do is the 2s complement 101. This MSB bit we have to invert it. So -3 in offset in 2s complement becomes -3 in offset binary with this bit inverted. Okay, rest all bits remain the same. So that is the conversion between straight binary to 2s complement to offset binary. Okay. So there are no questions in this. We'll proceed to the question section. So consider this question. I have KDs in Q 3.7 format, and the value is 3.7, right? So it is 10 bits, okay, and it is a sign format. So these are the bits before, these are corresponding to this before the decimal for the point, and the 7 bits are after that. Okay, this meeting will end in 1 minute, so I will stop the meeting and start the meeting. Enjoy them. Yes, can you calculate this value of KD? I guess
So it is 3.884.
yeah, so how to do this? This is 2 raised to 0, this 2 raised to 1, 2 raised to -1, 2 raised to -2, 2 raised to -4, 2 raised to -5. When you add all this under the exact value, I think it's allowed to be 3.8437. So we proceed to the next question.
This is not a little bit. Not
Now,
audible.
is it audible now? Hello? Is it audible?
Yes, sir.
Yeah.
Yes.
Okay.
Sir?
So, yeah.
Sir, in the last case, that the gain bandwidth ratio,
Yeah.
as you said, if we manage to keep the gain of the amp less than 1,
Okay.
then we can get the inductor current, the sense inductor current approximately equal to the actual current, right?
I don't know if the bandwidth can be greater than that unity gain bandwidth. That you'll have to check
Oh,
whether it's possible. I don't know. So usually
so bandwidth current.
in most cases you will not like what's the thing is sensing is this resistor value will be very low. RSH will be in milliohm. Say it is 5 milliohm or something. Okay, suppose your current was like 10 ampere. So 5 into 10 will be 50 millivolt. Okay, it's such a low value. Okay, now this 50 millivolt, you just take, suppose even if you use unity gain, IL sense will come to be 50 millivolt. Okay, if your IL sense comes to be 50 millivolt, it is such a low value. Your ADC also has a certain resolution. Suppose in case your ADC resolution was 10 millivolt, assume, then it is very, very poor. Like in large steps, suppose your inductor current is, so I'm saying if 10 ampere corresponds to 50 millivolt, that means 1 ampere corresponds to 5 millivolt. Okay. So, and suppose your ADC resolution is 10 millivolt. So it can only change, the ADC value can only change if the change in your inductor current is 2 ampere. And that is a very like large change. Okay. So, and in 50 millivolt range, there will be noise. Okay. Noise is something in sensing which is a big headache. So if at this low value of 50 millivolts, then the noise will like override your actual sensing. So that's why you usually, in most cases, your gain will be higher. Now, if you want to get rid of the noise, you will have to reduce the bandwidth. Okay, you'll have to reduce the bandwidth. And to reduce the bandwidth, they will connect these bypass capacitors. Okay, these capacitors are connected. I don't know whether there's a bypass capacitor, but these are like these filtering capacitors are there. So this will sort of reduce the high frequency noise. So this will reduce the bandwidth. Okay, that's right. And you cannot have bandwidth very, very high. You cannot have like I want to have bandwidth like 1000 to F switching frequency, or that it is not required. And another thing is the noise also will come. So in the sensing circuit, there will be noise. So you don't want your bandwidth also to be too high. So you need to limit the bandwidth as well. So that we are not told. I had not told it earlier, but also there is a requirement to limit the bandwidth to reduce the noise from affecting. And the main thing you require in sensing is you need to have a high signal to noise ratio. Okay. So for that, one of the reasons, so for that you use these filtering capacitors to reduce the noise, as well as you use higher gain, so that the signal value is at a higher magnitude as compared to your noise. Okay, so the noise won't dominate, your signal will dominate.
So if you want the actual IL sense equal to the IL, then bandwidth should not be less.
Yeah. See,
again, if you keep the bandwidth to be high, the noise will be coming out.
Yes.
Yeah. So we have to find a middle point.
Yeah,
of bandwidth.
Yeah.
How, sir? Is there a way to select that bandwidth, sir? Is there any method?
I don't
or
know.
by trial and error or practice?
Yeah, by trial and error practice actually. So like you can set the gain and all, you can design everything. First thing is the bandwidth should be greater than 10 FSW. That is your standard. Okay, then you want to also limit the bandwidth as well. So for that you connect these capacitors. Now in case you find that the noise is still more. Okay. So what you can do, you can increase the value of the capacitors. So when you increase the value of the capacitors, it will further reduce your bandwidth. So in that way, you can replace those capacitors with a higher value capacitor and thus further reduce the bandwidth. So these issues will come to you only when you make the board. As long as you don't make any board, you will not face these issues. So let us consider 5-bit. We'll ignore the term SAR ADC. It is just a ADC. So it is a ADC. So it has a V supply is 2 volt. My V supply is 2 volt. My span of my ADC is 2 volt. Okay. My input signal is 1.2 volt. Now the range of the digital output of my ADC can range between 0 to 2 raised to n minus 1. So 2 raised to 5 is how much? So this can range between 0 to 31. So this is in this decimal in an integer form. Okay, this is your integer form. So suppose this is my ADC whose span is 2 volt, and this is the digital output. So if I give it 0, it will give 0. If I give it 1, it will give a value of 32. It will give 15. If I give it 2, it will give a value 31. Okay. So what we will do is we will find how to find this equivalent. So this equivalent decimal number is equal to V in upon V span into 2 raised to n. So that will be equal to 1.2 divided by 2 into 2 raised to 5. So it is 1.2 into 2 raised to 4. So it is 1.2 into 16. So 1.2 into 16 comes out to be 19.2. So that's why we approximate, and it should be a integer, so we approximate to 19. So 19, if we have to convert it into digital value, So the digital representation of 19 will be how much? Could be 10011. 10011. Okay, so this should be the output of the ADC. So any doubts in this?
For 1 point, we're actually finding for 1.2 volts, what is the digital equivalent at the output, right?
Yeah, that's what you found. Yeah. One more thing, for one, it actually should be 16. Yeah. So next we'll proceed. How do we represent 98 as a 12-bit hexadecimal number? Okay. So I have 98. I want to represent it as a hexadecimal number. So how should I do this? So 12-bit. So 12-bit means it is hex, okay, 12 hex. It has value x, y, and z. So how should I proceed with this? How you do it is you divide 98 by 16.
By 16.
So you get 6. This is 6. 6. This is 96. Okay. Then this goes to 0. Okay, it's 20. You again do the 16, you get this 4, 14. I think I'm making mistakes on that.
So we divide by 16, we get 6 and the remainder is 2.
No, 2. Okay, okay.
So 62H.
Sure. So it will be 62H, you're saying? Okay, so it come to be 62. Okay, 62. Yeah, 62, yes. So this is my LSB, this is the next bit, and by this will be 0. Okay, because in 62 itself it is getting represented. Okay. So this is all beyond the point. This is all beyond the point. So that is not considered. Are there any
12-bit hexadecimal number.
Yeah, so that's why this is 4 bits, this is 4 bits, this is 4 bits. That's why I added the 0. Now we have to represent it in binary. It will be 12 B prime. This is 0, no? So 1, 2, 3, 4, 0. 6 in digital is actually 0, 1, 1, 0. So this is 1, 4, this is 1, 4, and 2 is 0, 0, 1, 0. This is 2. So this corresponds to 0, this corresponds to 6, this corresponds to 2. Okay, so this is how you represent a 98 in hexadecimal format as well as in binary format. Right? So I'll proceed. Now we consider certain Verilog questions as well. So I have a module test. Okay. This is my module test. It takes inputs X, Y, Z, it gives output G. Also I've defined certain Y as T, F, X bar, Y bar, etc. So my X bar is not of X. So I have X bar, which is coming from not of X. Okay. Next is I have T, which is AND of Y and Z. So Y and Z, the AND is coming up to be T. Next is not of G2, Y bar of Y. So this is Y comes here, this comes out to be Y bar. Right? Then I have AND of X bar and Y bar. So I have this goes in it. I will get F This is AND of X bar and Y bar. Then I have OR, therefore G, T, F. So I have OR gate, output is G, inputs are T and F. So my effective G can be represented as Y and Z. This Y and Z or plus X bar and Y bar. X bar and Y bar. Okay. Is this clear? How you represented in a Boolean logic expression. So now this is a question. Suppose this is my FPWM. Okay, this is my. I also have certain Q out. I have a Q out which is also drawn like this. This, this. So Q out is like a fixed duty ratio. Okay? Q out is like a fixed duty ratio. Then I have NE. Okay, NE is a number. If NE is a single bit number, it can have either value 0 or 1. So that assume it is 1. Okay, then it becomes 0, 1, 0. This is my NE. Then over here it becomes 1 and remains like this. Okay, this is my NE. So what does this code say? It says that if at the positive edge, that is at this edge of my FPWM, it will check, it will go in, okay, it will go in, it will check NE. If NE is 1, if NE has the value 1, then what will happen? My Q1 will be 0. So over here, regardless of what it was prior, my Q1 will be 0. So my Q1 over here, it is 0. It is 0 like this. Okay, at this positive edge. Okay, and let us assume that it was 1 prior. Let us assume it was 1 prior to that. This is my Q1. At the next positive edge, it will check. It will find that NE is 0. NE is 0 at this positive edge implies my Q1 should be high. So Q1 is high. The next positive edge, it will again check. Again, it will check if NE is still 0, so it will still remain high. Okay, it still remains high. Then the next positive edge of FPWM, it will check. It finds that NE is 1. Since NE is 1, that means your Q1 has to go low. So my Q1 has gone low in this case. Now, my Q gate is actually Q1 and Q out. So my Q gate which comes out will be for this format. It will be still 0. 0 into and so 0 dominates, so it is 0. At this case, it becomes 1. So it will have, as long as this is high, this will be high. Okay, when that goes low, if this is 0 and this is 1, so it is 0. Over here again it turns high, so it will come high. And when it goes 0, it will come like this. Okay. And then again at this instant, my Q1 has gone low, so it will continue to remain 0. This is my Q gate. Okay. So can anyone tell what sort of logic this represents? Like we did it last class, actually. So this actually represents pulse skipping modulation. Okay, when my error is 1, that is my V reference minus V out, which is my NE. NE is V reference minus V output when my error, okay, this is NE. and any is a sign bit. So when my output is greater than my V reference, that time my V error is less than 0, and if V error is less than 0, the N is MSB will be 1. So this corresponds to the logic for actually pulse skipping modulation. So in this, so if N is 1, that means my output voltage is greater than my reference voltage, and so I need to skip the pulse. So I need to skip the pulse. So I effectively generate a signal which depends on the logic. Okay, and it will skip the pulse accordingly. Okay. And in this case, when NE is 0, that means my output voltage is less than my reference voltage, and I need to charge it. So then I give the pulse. Okay, so this is the code. This is a code. I've just taken a small snippet of that code and I've showed it to you. Okay, so all these codes have come up based on these diagrams. So it is like you must realize that the code is not important. The diagram is important. Once you have the diagram, the timing diagram, then you translate the timing diagram into a logical code. Okay. Any queries in this? See, so this is the one of pulse skipping modulation. How we determine when to skip the pulse. So this is my fixed duty ratio pulse which is coming. This QPSM says whether my output voltage is less than my reference voltage. And this is the samples of output voltage which determine that. Okay, the samples of the output voltage will determine that. Based on this QPSM and QP, I get the actual gate signal. The gate signal side the inductor current rises, and then when it is off, it falls and it remains in DCM. Okay, it remains off. So this is the logic of digital pulse skipping modulation, DPSM. That line and the small snippet of that code I have shown over here. So any queries? Okay, so I'll proceed. Now, can you identify which gate this is? There is a truth table. So this is my A, this is my B, this is my X. Suppose A, B both are 0. If A, B both are 0, this is 0, this is 0. So that means this is on, this is on. So this is VDD. So this is 1. Okay, A, B, this is 1, 0. B is on, A is off. So this is again 1, 1, 0, it's also 1. If both are on, then it gets connected to ground, so this is 0. So this is a NAND gate. Okay. Then this is another circuit. So in the similar manner, you can do for this one as well. And this will be there actually this one is this whole part is actually my NAND gate. And this corresponds to a NOT gate. So effectively, this is an AND gate. Okay. So NAND gate is real, and this is the NAND gate. So the NAND gate is realized using 4 transistors, and the AND gate is realized using 6 transistors. Okay. So this is one case. Now we will consider boost converter. This is for finding out the delay. Okay, the delay in digital mode. We have boost converter. V in is 20 volt. V output is 50 volt. Switching frequency is 100 kilohertz. Assume it is in digital pulse width modulation. So your duty ratio, what is your duty ratio? Will be what? For a boost converter, what is the duty ratio expression? see V out is equal to V in upon minus D. V out upon V in is equal to 1 upon 1 minus D. Then V out is what 50. 50 by 20. That is 1 upon 1 minus D. So 5 to get cancelled. So 2.5 is equal to 1 upon 1 minus D. So this becomes 1 minus D is 0.4. So D is 0.6. Okay. The delay in digital domain is D into the time period plus your ADC delay. So D into time period, so this is 0.6 into your time period, that is 10 microsecond. Your ADC delay is 100 nanosecond, 100 nanoseconds corresponds to 0.1 microsecond. So this is 6.1 microsecond. So this is your overall delay. Okay.
The T, capital T comes from this switching frequency. No?
Yeah, from the switching frequency.
Sir, this delay that we are giving, the sampling delay, is that this delay? This D into T.
No. The D into T.
Yeah. So that delay is.
I don't know, that delay, I think that delay is actually due to the DPWM modulator. When you find a transfer function for digital pulse width modulator, you will get that delay, DT. This I think was taught in the second week, I think. The second week. For an, you see, this is your modulator, okay? And this is your RAM, V RAM. This is your V max. And your duty ratio and analog domain is actually V. This is your V control. Duty ratio in analog domain is V con upon V max. Okay, so this is your effectively your modulator gain. But in digital domain, when you go, you will also get an additional e raised to minus dt that comes. So because of that, there's this delay dt. Okay.
Okay.
Now we are doing digital control and you will do discrete time model. Okay, there's a high level thing, but we'll just consider the steps. We figure about the steps. So can you arrange the steps to find the discrete time small signal model of a DC-DC converter? What would be the steps? The first step is you will write the state space matrices. Step 1. You will write the state space matrices for the converter for the various operating modes. That is when the main switch is on, the main switch is off. And you can even do it for discontinuous conduction mode when both the switches are off. Then what you will do, you will find the state space solution from one operating mode to the other and determine the overall large signal discrete time model you will find. Then what you will do? Then you will perturb this nonlinear equation to find the linearized dynamics. The third point. The small signal model is the linearized dynamics around a particular operating point. Then you will take the Z transform of the corresponding equation, and then you will get a discrete time small signal model or a discrete time transfer function of that DC-DC converter around that operating point. Okay, so these are the steps. So this question like I prepared when I conducted a session for that week, I think week 5. So discrete time model is a very complicated thing. So I just wanted to give you the brief steps. So just briefly re-jog it to your memory. Next, we consider boost converter, right? These are the input specifications of the boost converter. And now I have to determine the controller parameters, and I will consider type 2 compensator. And as we have told, for boost converter, the bandwidth is the minimum of f RHP by 3 or f SSW by 10. Okay, so this is the bandwidth which you must consider so that your model is valid. Your small signal model is valid. So now how will you proceed? So they have told you must use peak current mode control. Peak current mode control you must use. You must make a controller. You must consider type 2 compensator, and you must take the crossover frequency, that is your bandwidth frequency, with a third of the RHP zero, f RHP by 3. And what? So that we have to do. Okay. So what is the procedure? So in this case, my GVC of S, the transfer function for peak current mode control buck converter, is K into G into 1 minus S upon omega RHP into 1 plus S upon omega ESR upon 1 plus S omega pole. Okay, the pole of it. So now what is my kg? My DC gain. So kg is my DC gain. So the formula for kg is equal to R into 1 minus D upon 2. My omega RHP formula is actually R into 1 minus D square by L. My omega ESR formula is 1 upon R3 into C. My omega P is 1 upon R plus 2RC into C. Okay, so can you find these values? What will be the values?
D is 0.34.
Okay. So the first step is we have to calculate D. So D is 0.34.
Kg is 0.17. Kg is 0.17.
Kg is
Oh, sorry.
0.17.
Sorry. 0.33.
0.33, right? Yeah.
Which is 217.8 into the power 3.
This is 217.8 into 10 to the power 3. Omega ESR
6.
hmm?
210 to the power 6.
Okay. So this is 2 to 10 to the power 6. And omega P is
0.
so there's a mistake. Omega P is 2 upon R plus 2 R C. What does omega p come out to be?
So,
Hmm? It will come out to
19801.
19802. Okay. And this is in radians per second. Okay, so this is the transfer function of your plant. Okay. Then you will have a controller. So type 2 compensator they have told. So type 2 compensators GC of S is KC to 1 plus S upon omega CZ. This is your controller 0. Type 2. So there's one pole at origin and one pole omega controller pole. So what do we do is GBC of S into GC of S, and you consider that the feedback gain is unity. So my loop gain is the product of my plant transfer function and my controller transfer function. That is Kg to 1 plus OS upon omega ESR 1 minus S upon omega RHP upon 1 plus S upon omega P into this GC of S. Kc 1 plus S upon omega controller 0 upon 1 plus S upon omega controller pole into S. So what we do is, this is negligible, okay? Omega ESR is very, very high, very, very high. So this is neglected. So this part gets neglected, okay? Then we cancel this pole with this 0. And we place omega controller pole to be at the omega RHP in coincidence with the RHP pole. So that it becomes Kg into Kc upon S into 1 minus S upon omega RHP upon 1 plus S upon omega RHP. Now, when we take the product, the magnitude GBC J omega into GC of J omega, this magnitude is 1. Okay, magnitude is 1. So that's why the magnitude will be Kg into Kc upon J omega. The other one, magnitude is 1. So that is Kg into Kc upon omega. Now at the crossover frequency, crossover frequency is when the loop gain becomes equal to 1. That frequency omega is known as your omega crossover. So your omega crossover frequency is, so this becomes equal to 1. So omega crossover frequency is equal to Kg into Kc. So we determine Kc is equal to omega crossover frequency upon K into G. Okay, so in this way, we have determined your transfer function of your controller. We found what should be Kc. Your controller 0, we told that it should cancel out my controller pole, and omega Cp must be in coincidence with my omega RHP. So this way you can find the transfer function of your type 2 compensator. Okay. And then you can find the phase margin, as well as if you consider delay, what would be the effect. So just excuse me for 1 minute. Okay. So we'll proceed to the next question. Let us assume Kc is in Q3.8. Oh, yes, yeah.
We are saying about type 2 compensator.
Hmm.
Sir, but here in this, we have this S power to be on only.
Where?
GC of S.
Yeah, so
The denominator S.
there are two poles, right? There are two poles, so it becomes type 2. It is not a type 2 system. This is a different thing. This is a type 2 controller, type 2 compensator. It's not a type 2 system. Type 2 system is where there are two poles at the origin, right?
Okay, sir.
So we will consider KP to be in Q3.8 format and V error is in Q1.9 format. So my VCon is KP into V error. So now this is Q format multiplication. So this is Q3.8 multiplied by Q1.9. So my effective Q format will be Q3 plus 1, Q3 plus 1 minus 1 dot 8 plus 9. So it comes out to be Q3.17. Okay. So why does this minus 1 happen? Because there are two sign bits. Okay. We don't require both sign bits. So we have to discard one sign bit. So my effective Q format is 3.17. So my VCon comes out to be Q3.17. Now this VCon has to be compared with a counter. Counter is of format Q3.15. So this VCon, which is in the format of Q3.17, has to be converted in format Q3.15. So to do that, what we will do, we will discard the two LSBs, okay? Two LSBs we will discard. The last two bits we will discard. So in this way, we will make the VCon to be of the format of Q3.15. Okay.
In order to compare, we are making the Q values equal.
Yeah, the Q format should be equal
Mhm.
for comparison. Now, let us consider a 10-bit ADC. Okay, my KP is in Q2.8 format and my KI is in Q3.7 format. What will be the Q format of my endpoint after resizing? So this is a KP, this KI. Okay, both are there. KP and KI are there. So it is a 10-bit ADC. Let's consider the ADC service using. So the V output signal is of the format Q1.9. So my V error signal is also of the format Q1.9. So the part corresponding to a proportional part is Kp into V error. So that is Q1.9 into Q2.8, which comes out to be Q1 plus 2 minus 1 dot 8 plus 9. So that is Q2.17. Okay, this Q2.17. Part corresponding to my integral is Ki into V error. Okay, Ki into V error plus there's this UI previous, etc. Now you must remember for this, for an addition, both Q formats, this Qn1 dot m1 and this Qn2 dot m2, both n1 and n2, n1 should be equal to n2 and n1 should be equal to m2. So we assume that this has been taken into account, so we neglect this. So Ki into V error when we do, that is Q into 3.7, Q into 3.7 into Q into 1.9. That corresponds to Q3.16. So we get Q3.16. So part corresponding to my integral is Q3.16, part corresponding to my proportional is Q2.17. Now Ncon is proportional plus integral. But I cannot add Q2.17 to Q3.16. That is not possible. So I have to convert it in, both have to be converted to the same format. So in this one, I will add to the MSBs. Okay, I will add to the MSBs. So I will pad the MSBs. Okay, it's known as padding the MSB. So whatever bits it has less, okay, I will add 1, 1, 1, 1, all ones. And when you do that, we have shown in the week 7 or 8 how the value remains the same, although we will add extra bits. Okay, so this we will convert it into Q3.17. And in this, we will pad the LSBs with 0. We will add zeros to the LSB. So this also will convert to Q3.17. So my effective format of Ncon will be Q3.17. Okay.
So the greatest of the two in both the sides of the decimal should be taken, right?
Yeah. Yes. Yes. Okay. Yeah.
Sir, this video will be recorded.
Yeah. This video also I'll upload.
I don't think in the they have no space for in the NPTEL.
Okay, but you have my YouTube channel link,
Channel,
right?
yeah. Yes.
So you can do it. I'll upload there. Okay. So, so now we'll proceed to the last question. So I'll just give you the brief steps on how to do that and let you guys to solve it actually. So we have a buck converter. Okay. We the following parameters. These are parameters which are given. So we want to find the phase margin when we are performing VMC. So we are doing voltage mode control. It is a buck converter. We are doing pole zero cancellation, and we are taking the crossover frequency to be a tenth of the switching frequency. So my crossover frequency is 2 pi FSW by 10 that we have determined. Okay, so what we will do is this is voltage mode control. So my transfer function required is GVD of S. That for a buck converter, it is actually given by Vin upon alpha. This is my DC gain, that is into 1 plus S upon omega ESR upon 1 plus S upon Q omega naught plus S square upon omega naught square. Okay, this is my GVD of S. Then where my alpha is given by R plus R equivalent upon R. My omega ESR is given by 1 upon RC into C. My omega naught is equal to 1 by root LC into square root of R plus RE upon R plus RC. Okay. And my Q is given by alpha into RC plus RE upon ZC plus ZC upon R, the inverse into alpha. Okay, so these are the formulas which you must use to find GVD of S. Okay, this is a standard formula for the buck converter considering the parasitics as well, because the parasitics have been included in this question. So this I find GVD of S. They are saying now you must do pole zero cancellation with voltage mode control. We will use a PID controller. So we will use a realizable PID controller. So my GC of S is KP plus KI upon S plus KDS into tau ds plus 1. So when you do the shuffling and all, you will get it to be of the form S, it will be of the form KI. Okay. Let us see what it comes out with. KP tau ds square plus S plus KI tau ds plus 1 plus KDS square S into tau ds plus 1. That becomes S square to KP tau d plus KD plus S into KP plus KI, KP plus KI into tau d, KP plus KI into tau d plus KI. Okay, upon S into tau d S plus 1. So that comes out to be KI into 1 plus K1S plus K2S square into S into tau d S plus 1. So what we do, we again find a loop transfer function, that is GC of S into GVD of S. So this is second order polynomial, and this is a first order polynomial. What we will do is, we will cancel out this polynomial with this 0. Okay, 0 of the transfer function with this pole. With this pole, we will cancel out. And this numerator of the controller, I will cancel out with the denominator of this. So my effective loop transfer function will be Vn upon alpha into Ki into S into tau d, no, S into S. Yeah, so this is my effective loop transfer function. So again, like we did in the previous case, we do Gc of j omega, Gvt of j omega, the magnitude Vn upon alpha into Ki upon omega, okay? And then at omega, which is the crossover frequency, this will be Vn upon alpha into Ki upon omega crossover is 1. So we get the omega crossover frequency to be Vn upon alpha into Ki. Okay. So this is how we can get, okay, omega crossover frequency is given. So based on that, we get Ki. And because we had done full zero cancellation, we can get K1 and K2. And from that, we will get the value of Kp and Kd. So that is how we get the Kp, Ki, Kd. We get Kp, Ki, and Kd. Then we have to convert it into digital domain. Okay, because we are doing implementing in digital domain. So Kp remains the same. Ki digital will be Ki into Ts, and Kd digital will be Kd upon Ts. Okay, so that's how you find the PID controller gains, and then you use the time period which is required, and you get the digital values of the controller so that you can implement that in the digital platform. Okay. So also you can also consider sampling delay. Also you can consider some 0.2 microsecond, and so if you consider the sampling delay, plus you'll have to consider the dt plus 0.2 microsecond. You have to add. This is your overall time delay you must add, and when you do that, your phase margin will reduce. Okay, the phase margin will reduce. So you can do that part. I will leave it up to you. Okay. Or let me just tell it off. Let me just tell it off. So let's consider a case where there's no delay. So my G loop of S came out to be Vn upon alpha into Ki upon S, right? So when we convert into G loop of J omega, it will be Vn upon alpha into Ki upon J omega. So when we find the angle of G loop of J omega at the crossover frequency, it will come out to be minus 90 degree. Minus 90 degree, why? Because of the J. So the angular contribution at omega crossover frequency is minus 90 degree. So my phase margin is 180 plus angle of G loop J omega C. So 180 minus 90 means my phase margin is 90 degree. So this is the phase margin when there's no delay. But now we added delay. So if we add a delay, that becomes e raised to minus s time delay. When you add that, this will become e raised to minus j omega t t. When that is there, the angular contribution will be minus 90 degree minus omega c t d. Okay. So then my phase margin will then in that case be 90 degree minus omega c t d. Okay. And by TD, what is my TD? It is my duty ratio into the time period plus that delay due to my ADC, TADC, sampling delay, that is 0.2 microsecond. So you substitute the values and then you will get what is the phase margin and everything. Okay, so are there any queries in this?
So delay will reduce the phase margin further.
Yes, so delay reduces the phase margin, and higher the phase margin, more stable it is. As I told also, I think I mentioned in week 11 that thing about the Maximovich book. I referred to some thing, chapter 11 or something, about how this like phase margin is used as a test for stability everything. That way. So like, cause stability is a very important thing in control systems. You want your algorithm, your control strategy to be stable. So for that, you use the phase margin test. Okay. So these are some set of questions which I had,
Sir?
made cases.
Sir, if our phase margin, if we keep the phase margin within the value what we are getting, then the system, even though it experiences disturbance, it can come back to its stable operating point, right? That is what we want.
See, when you give a disturbance, how your system will respond. Okay. That is determined by the phase margin. So in case your phase margin was low, assume your phase margin is low, and you give a like some sort of disturbance occurs. So if your phase margin is low, what will happen? Assume this is your output step. Okay, your output current has increased. There's a step up transient. So what happens? Your output voltage will reduce it. Your output voltage will reduce and will come back. This is what we prefer it to be. But in some cases, if the phase margin is poor, your output voltage will go like this. Okay, it will go like this. These peaks will be too much. Okay, so if that will then violate the constraints which we want. That you want the voltage to be within certain limits. That is why the phase margin is important. Okay.
So phase margin should not be lower enough.
Phase,
should not be lower.
Yeah, it is standard practice like around 45 to 75 degrees. These exact values depend on the application, everything, based on that. But if you have a very high phase margin, it is another problem because then your response will be slow. If phase margin is very high, it will be a slow, sluggish response. Okay. So phase margin should not be very high, neither should it be very low as well. Okay. But phase margin should always be positive.
Behavior is like can you please explain briefly why this?
Okay. See, like phase margin is related to the damping present in your system. So if your phase margin is poor, there will be more oscillations. Yeah, zeta. Okay. So if the phase margin is less, the oscillations will be more, which is not desirable. Okay. And if your phase margin is a good amount, it will come like this. But if your phase margin is very, very high, that means your damping zeta is greater than 1. So it becomes an overdamped response. So if you know that known for a step input, underdamped response is like this. Okay. Overdamped response will go like this. Okay. And your critically damped will go somewhat like this. Okay. So now which is faster? Your underdamped response is faster than this. Okay, your overdamped response is slower than this critically damped. So your underdamped response is faster. That is known. So, but the case is that oscillation should not be too high. So usually we take zeta we do it in such a case that it is underdamped. No doubt it is underdamped, but the oscillations are not that high.
Sir, in the case, if you take the S-plane, in that we keep the poles closer to the real axis, but it has imaginary value.
So
is that the response?
Yes, if it is underdamped, that means the poles are complex conjugates. That is correct. Now,
but it will be closer. If you want the oscillation to be less, then it has to be closer to real axis.
No. Oscillation to be less in the sense means, see, for a second, let us. You're talking about this is your SN, right? This is your S-plane, this is your sigma, this is your j omega, right? So if it is critically damped case means both your poles are here. If it is a overdamped case, means I don't know exactly, but one pole might be here, another pole might be here, something like that. Okay. If it is underdamped case, then one pole will be over here, other pole will be a complex conjugate. Okay, these are all should be poles, not zeros. Okay, these are all poles. So, and if so, your pole in the is given by sigma plus j omega. So your omega determines the frequency of those oscillations. As I showed, these are the oscillations. The frequency of these oscillations are determined by the pole location, j omega, the imaginary part. But if you see, if you give a step response, your output will behave like this. There will be a damped sinusoidal term. This is a damped thing. That is determined by your sigma. This sigma. Okay, sigma into t. So, uh, 1 minute. This I think is e raised to minus. I don't know exactly, but something related to sigma is determined. So if sigma is small,
Okay.
sigma is small, then it will take more time. Then the damping is poor, and it will take more time to decay. But if your sigma is large, then it will decay faster. It will decay fast. Okay, so if you want it to decay fast, it means your pole should be further right. Okay, further left, further left. Okay, your pole should be further.
Okay.
If it is brought closer over here, you just think, no, if it's brought closer over here, that means it's coming closer to the right half plane. As it comes closer to the right half plane, it is going towards the unstable region. So if you want it to be stable, you must move the poles further left. Okay.
Sir, now if we correlate with the phase margin, if a phase margin is low, we are saying we will get oscillatory response. So if the phase margin is low, here we can consider the pole is closer to the imaginary axis.
No. Phase margin actually, what was the thing? I actually forgot what was the thing. Phase margin does not depend on the this. I don't exactly remember. Your pole is given by minus theta omega n plus minus j omega d. It is given by minus theta omega n plus j omega n square root of 1 minus zeta square. Your phase, okay. This was a 100 system. So this angle theta something, this angle theta is given by this part, imaginary part upon the real part. So that will be square root of 1 minus zeta square upon zeta. So, and this is relation for phase margin is also related to zeta in some case. And based on that, so phase margin is related to zeta and zeta is related to this angle theta. So there's some relation. Based on that, you just cannot say that if you move it further right, the phase margin will improve or something. That you'll have to check actually. Mathematically, you'll have to check. Okay. One more thing I forgot to mention is in this question, in your loop, there will also be FM also will be there. FM also will be there. Okay, FM also has to be there. That is the modulator gain. FM is your modulator gain. Okay, so this phase margin thing you'll have to check actually. You'll have to check some standard control textbooks to get the exact correlation between pole location and phase margin. Okay, and there's one more thing about PID controller. So what is the effect of each gain? So if I increase KP, my overshoot will increase. But it has a minimal effect on my settling time. Okay, it has a minimal effect on my settling time. And it will reduce my steady state error. If I increase Ki, my overshoot will increase. My settling time also will increase. But my steady state error, it can drive it to 0. Now, if I increase KD, what it does, KD improves the damping. It improves the damping. Okay, it will improve the damping. So my overshoot will reduce. My settling time also will reduce. But it has negligible impact on my steady state error.
Sir, this thing, can we intuitively say something like using the S-plane or?
Intuitively, like KD, if you add derivative control and then when you find the transfer function, you will find this for KD. I remember, for others I'm not able to say. It will come S square plus S into your original. Suppose it was 2 zeta omega n plus tau d comes in, something like this. Okay, plus tau d plus omega squared, something like that. So this tau d will sort of, increase the effective zeta. So that in that sense, your KD will sort of improve your damping. And because it improves the damping, your overshoot and settling time reduce. And see, like KD, why in the steady state error, KD has negligible impact is because it is just differentiating, right? KD is basically KD into d by ds, right? Into your V error. So in steady state, if your V error is like 0, tending to 0, this derivative of 0 is 0. Okay, so that's why KD has negligible impact in steady state. And why integral control reduces the steady state? Now you see a plant. Suppose this is my reference, okay? This is my plus, this is my feedback signal. This is my controller. Suppose this was just proportional control. And this is my plant GP of S, okay? This is my output. Let us consider unity gain sensing. So this is my error. So my error goes to my proportional control KP. So to get my output, say 5, this should have some value, say around 1. Okay, and suppose my KP was 100. That means my error has to be 0.01. So error has to be 0.01 into this KP 100 to bring 1 so that my output will be at 5. Okay, so my output will not exactly be at 5. It will be at around some 4.4, 4.99, something like that. While my reference is at 5. So in that case, my system will reach a steady state. To reach a steady state with some error being present. And as you increase the KP, your error will reduce. If the KP is made 1000, your error will be 0.001. Okay, so this is the effect of proportional control. But if I had same thing, I had my reference plus minus my output. Yes, this is my KP. KP part is there, as well as I had Ki upon S. Okay, that is added up, and that goes to my plant GP of S. And this is the output. And this comes over here. And this is my error. So in steady state, just consider steady state. My error, assume what actually happens is this suppose error is 0. This will have output 0, but this will not have output 0. It will have a history term. And that history term, it will give the value of 0.01 or some value of 1. It will get this value of 1. That what value of 1 was required to get the output of 5, it will get, because my integrator has a history term. So even though the error is 0 over here, my integrator can give the value 1. It can give the value 1 because it is the history term. History of the previous errors has been summed up until I finally get a certain value, which will make my plant to reach the steady state value. Okay, so that is the advantage of an integral controller. That is how it drives the error to 0, because it is summing up the error. So when suppose my error was like around 0.01, then error becomes like 0.005, minus 0.005. All these things will add up. It will add it up such that, and it will drive the system in such a way that the error goes to 0. And this, you can even see that what the integral control does, it actually increases the type of the system. So when it increases the type of the system, it brings a error to the steady state error, can drive it to 0. Okay.
Yes.
So with that, we'll end for today. So I will upload this presentation on YouTube. This video. Okay. So I'll stop sharing. Yeah. So any other questions or anything?
Sir.
Yeah. Yes. Yes.
Sir, thanks for all the sessions you have taken.
Oh, yeah.
We have
Welcome.
gained more knowledge from you.
Yeah.
Yeah.
Thank you for joining. Yeah.
And all the best for your PhD, sir.
Yeah. Thanks a lot. Okay. So if there are no other questions, I'll end the meeting. Huh? Yeah. So it was also fun teaching. Okay, you guys asked good questions, and it was helpful for me also to like some things I'll miss out. You guys pointed out, and it was actually interactive. So previously, last semester, I'd done some other NPTEL thing for network analysis, and at the final session, like no one was joining, so it was very boring. It's just me talking. So it was good actually that you guys were asking doubts and questions. Yeah. Okay. Okay, so thank you. I'll end it. Huh? Good night.
Good night, sir. Thank you.
Yeah. Bye.